Hi, I'm Johannes, and I'll be talking about who instruments the instrumenters. An interesting talk down the rabbit hole of trying to understand code instrumentation. So, what is code instrumentation? Code instrumentation means, in its most basic form, that taking some Java code or some Java application and transforming it into another application. And you could see this like when I work on my application, I'm essentially transforming the code all the time, and then I'm maybe pushing it to Git or maybe pushing it somewhere else, and thereby modifying the code and also transforming it. But we can use this typically for example, to replace a method call, like the called method A, with a log statement and then the method call, and can thereby log or instrument the method call and see when it was called or do other things. It's pretty cool, but typically in Java we don't only use it on Java code. In most cases we only care about the bytecode, because for many libraries we might not even have the Java code. So what we do, we compile our Java code down to bytecode, and then in the JVM, when it's loaded, we instrument it in the JVM itself, so that the executed bytecode is not really the bytecode that we pushed in. If you're wondering what tools are using like on the Java source code level transformations, one of these is Lombok. They essentially created a Java compile plugin and they work on this level. And so with Lombok, the bytecode that's actually on your disk in your jar is different from the bytecode that would have been originally produced. But I'm not talking about this because that's a whole nother topic, and I can assure you writing compiler plugins is not nice. I've done it before, please don't do it. You need lots of internal APIs that might change all the time, but what we're really talking about here is about the transformation that happens in the JVM. So why would we need it? Why would you as a normal developer need to understand what code instrumentation is in Java? I'll be showing you in the following a few use cases where you could use and hopefully use it already. One is code coverage. So what does it do? Consider we have a simple example. It's our discount calculator, and what it essentially does, it calculates the discount that someone gets for a specific price, depending on whether he or she is a member or not. And you see it here, it checks if the price is above 100, members get like 20 euros discount, non-members 10, and if it's below 100, members get 5, and non-members get nothing. So we write this in our application, and then we write the test case that just tests a few test cases here. But what we wonder is, are all lines in this code executed? Are all conditions executed? For example, is the line is member 20 and then 10, is this executed? And how do we find it out? A simple way would be, if we don't know about code instrumentation and tooling, we could just do simple printf debugging. So essentially we create a log statement in everything. Oh, interesting. We create a log statement in everything, and then we see, oh, the log statement for the middle line, this isn't printed, so hey, cool, we didn't execute it. But that's really hard manually to do. What we typically do is we use a tool that offers it. And this tool here that I used, it shows us, oh, this line is red, so it's not executed during our tests. Does anyone know what tool I used? Have you used it before? Yes, it's JaCoCo. It's like the OG tool that has been there before I started developing Java, and we see in a minute what problems come with supporting really old Java versions still now. They apparently still support Java 1.5 in the current version. I hope nobody of you uses Java 1.5 in production. If you do, please. If you use Java 8 still, please, but okay, that's fine. But I hope none of you uses Java 1.5. But if you do, JaCoCo is here for you. You can use it to do code coverage. So another tool that you might have used testing us on the range is Mockito. It's one of the most popular mocking frameworks out there, and here's a simple example that we'll look into in the next few slides too. Is we essentially mock our list, and we then add one to a list and then check whether add one is called. Then we could also use it for monitoring. There have been a few talks today on telemetry and more, and this is essentially what's used here. So they use, and also other tools from the different monitoring vendors, they use bytecode instrumentation to see which database calls are made and such. And then we also have other use cases. For example, use cases that might sound familiar, for example, profiling. So how would you profile a method here? And I've done it many, many times. What you just do is you record the start time at the beginning of the method and then print the elapsed time. In more generic way, would you log the entry and log the exit, and then your library takes care of this. And that's a pretty simple profile. You could write a profile using instrumentation and it would work, and it would be a nice profiler. And there are profiles out there that still use this. Of course, you could also create a debugger. Consider in a time, consider for a time that we don't have any Java debuggers and you want to create your own. And what you could do is take your code here, you just insert a debugging method call in front of everything, in front of every line, and then in this debugging method you check, oh, the current line that we are, should we stop there? Should we open a shell? And yeah, that's obviously not done in Java. Anyone knows the language where this has been done internally? It's of course Python. So that's essentially how Python worked till one of the most recent versions, that when you use the debugger, you essentially modified the internal bytecode so that in front of every line there was this check, should I do some debugging? If you want to learn more about this Python stuff, I wrote 3 blog posts on this topic. It's quite fascinating, but heavily. We are in Java, so we don't use this and with pro debugging. But you see, we could use these instrumentations tool to do many things, and probably more. So I also wrote a tool which you can use to see all the unused classes, only using instrumentation APIs. Who am I? I'm Johannes Bechberger, as I told you in the beginning, but what do I do if I don't stand in front of the stage and talk to people? I work at Submachine. We're one of the cool open source projects of SAP, and we're one of the biggest contributors to the OpenJK, so I'm actually working on Java all the time. For example, today when I sat in the speakers lounge, I worked on a new Java profiler that's hopefully upcoming, fingers crossed, it gets into JDK 25, let's see. But I'm working on this. We're doing many cool other stuff. So back to the topic, how does the implementation work? Because I've shown you before, we can use it, but you might wonder how the different tools works. And for one, what we use here is agents. So actually, when I wrote the talk title, like who instruments the instrumenters, it's actually who instruments the instrumentation agents. What is an agent? We can pass an agent on the command line via -java agent, and then pass the jar and then the args. And an agent is essentially like a bike computer that you attach to your bike, but here it's a small program that you attach to your JVM. And that runs alongside. It has a different class loader, but it runs inside essentially the heap of your JVM alongside as a thread. So what we typically do, we use these agents to add transformers, and these transformers transform the bytecode when it comes in. For example, when a class is newly loaded, or when you tell a class, hey, please retransform this class. For example, in this here, consider here we create now a simple example application where we just use the result of calculate discount. But what we want to do, we want to log this. So every time we use the calculator method to calculate the discount, we want to print which parameters are passed at its use for some logging purposes. And how can we do it? We can use a transformer for this. Transformer agent on its most basic level consists of a pre-main method. This is called by Java when we pass the agent here on the command line. And then what does the pre-main method get passed? It gets parsed the arguments and also gets passed the instrumentation object. This instrumentation object is like the most powerful thing in Java agent development because we can do lots of interesting stuff with it. One of the things is we can add a transformer, and that's pretty helpful. So we can add a discount transformer, and this is then called whenever a class is newly loaded. To quote the documentation for class file transformer, essentially an agent registers an implementation of this interface using the add transformer method so that the transform method of the transformer is invoked every time a class is loaded, redefined, or retransformed. So how does this API look like that we implement? So that's the version without modules, but there's also a version with, but that's the simplest version here. We get past the class loader. So which class loader tried to load this class? Which class loader does this class belong that we're loading? We're getting the class name. That's always helpful to know how the name of the class. Then we're getting a class object if this class has already been in the JVM, so essentially if we're retransforming it, because if the JVM just loaded the class, we don't have a class object, obviously. And then we get a protection domain that's related to security, and then we get the bytes, so that's just the class files. But who of you can read Java bytecode fluently? None of you. Good. Especially like I give you a byte array and you tell me like, oh, I modified this bit. No, it's better. No, it's really hard. Even with libraries like ASM, like the web ASM library, like the object ASM library, it's still really hard. And it makes no sense to fiddle with it because you spend like a minute of writing the code and then a week of debugging. So people had these problems before, and one of the libraries that helps with this is Java Assist. It's a library from like the JBoss application server space, and this essentially allows us to write Java code and insert it directly, and this compiles down the Java code to bytecode and inserts it, and it makes it so much easier to work with. And of course, there's the Bytecode library that, for example, people like Mockito, the libraries of Mockito use, and it's also a really awesome library that takes care of this, but I'm focusing on Java Assist because it's, in my opinion, for these small examples, much more suitable, and it has a slightly smaller API. But anyway, so what we do here? We have our transform method. We get these bytes in, but we need to do something with the bytes. So what we first do, we create a class pool that's like needed by Java Assist, but then we can create a class object, like a CT class object, which we then can use to modify, and we can iterate over it, for example, getting all the methods in this class object, and then in the end, when we're finished with it, we can just transform it to bytecode. How does the transform then actually work? So we create an expression editor, which is essentially a visitor that can modify the bytecode, and then we just iterate over all declared methods and instrument them. But of course, that's something that many people do, iterating over all methods and modifying the expressions in there, so they also added a method instrument on the class itself, and this then calls this expression editor on all constructors and all methods. So how does it work? It's really pretty simple. We just check, oh, is this a method call that we care about? So is this the method call of like calculate discount? And if so, we replace this method call. And what you see here, we have like our system.out.println. The dollar signs like $1 is like the first argument, $2 is the second argument. Then we just, because this expression has a return value, we store it in $_, and then we just call the method call itself with its arguments here, and that's all. And we have like a instrumentation agent in like under 100 lines of code, and that's pretty helpful. We can use this to modify things, to log parameters, to do much more. And that's one of the cool things of the Java ecosystem, because Java allows us to do this. Many other languages, it would be much harder, but here we have a specified API, and it grows and gets useful every day. But back to our use cases. So you saw before we had code coverage, ta-da, as before with JaCoCo. So you might wonder how this works, and that's why you probably are here. So to quote Juvenal, a Roman poet, quis custodiet ipsos custodes, who watches the watchman in his satires that he wrote 2,000 years ago. So essentially, who instruments the instrumenters? And I was essentially nerd sniped a year ago when I was in Canada meeting Mikael Franker at a nice conference, Kanfu, and he told me, like, couldn't we just look up what the instrumenters are really doing? And I wrote the meta agent. This is an instrumenting agent for instrumenting agents, which is a mouthful, but essentially what it does, you saw before that we can transform method calls, but instead of instrumenting like an arbitrary calculate discount method, so what you see here, we have this, we call on the instrumentation object, we call the method addTransformer to addTransformer. We could just instrument this. So could instrument a method that adds transformers and add our own transformer. So we replace this with the technique you've seen before, and replace it with instrumentation handler dot add transformer, and that does the magic. So what does it do? And that's a simplified version here, but what you essentially do, it adds a transformer, of course, because we need to add one. Otherwise, we would hamper the functionality of the transformer. But what we do then, we get also our class file buffer in, we clone it to get the old class file buffer. Then we call the transformer with all the arguments. That's fine, we get a current. Then we record a diff if there is any. So we record both bytecodes, the old and the new, and then we return the new bytecode. And that way we record what every transformer did to every class, and that's pretty helpful because we can see what the transformers are doing. And then, of course, because Java bytecode is hard to read, we throw it into FindFlow, which is essentially a fork of the FernFlow project that is used by IntelliJ to decompile bytecode into Java code. As we see in a minute, only works good on basic code, and some of the code that's generated by instrumentation agents is not that simple, but more on that in a minute. So what I then created is an agent that uses this whole technique, and when you run it, it opens a server on port 7071. You got loads of features. We see them later in the live demo. But what we're interested in is that we can get a list of classes that are, we can get a list of all the classes and decompile classes itself. And also see how they are changed. So for example, this is our discount method that you saw before, like to calculate discount. And now we're seeing how JaCoCo changes them. And for one, we see that JaCoCo also modifies the default constructor. So you see here in green what it changed. That's just normal diff view. You see here what it does. It essentially gets a Boolean object from somewhere that's probably related to the method. Then you see later, okay, it calls a superconstructor because that's what all constructors do by default. And then when we executed like the zeroed line of the constructor, we just write through in this Boolean. The funny thing is we didn't write anything there, so we didn't write the default constructor, but you see here it's still noted as being executed. So don't trust coverage tools too much. They still have things that are unexpected, as you see here. But anyway, so more interesting is probably the calculate discount method, and that's how it looked like. It's really big, but essentially what it does, in front of every line is like, oh, I've executed the line. I'm setting a boolean in this bool array. And that's a pretty cool solution because we don't have any method calls. But where does this boolean come from, you might ask? This boolean comes from a method called JaCoCo init that's essentially called when the class is first used. And so we essentially ask the JaCoCo data object, hey, please give us an object. And what we do, you see here that the JaCoCo, and so what we see here is that we call the equals method on the JaCoCo data object and pass into this our own object that contains some data. Essentially, it details our method. And then another thing, and I'll come back to the slide in a minute, but is that, of course, you saw here that this method call looked weird because it had like JaCoCo data string somewhere. It doesn't look like proper Java, and that's because it isn't what's really happening. So if you look at the bytecode closely, you might see if you use it, they essentially loads a constant from somewhere, that it loads some value and that it doesn't call anything. Because beware, the decompilation gives you only an educated guess. So back to our example here. So you might wonder, how does the JaCoCo object look like? It's pretty simple. It only has an object data. But how would we get then these Boolean values? You see it here, we only calling like equals here. Okay, some background on the equals method. Usually, if we implement the equals method, we need to essentially ensure 4 properties. It should be reflexive. So if you call if you call x dot equals x, it should be true. It should be symmetric. So x equals y should be the same as y equals x. It should be transitive. So if x equals y and y equals z, then x should equal z, and it should be kind of consistent. So if you call x equals y at some point in time, and then nothing changed on both objects, you call another time, it should also be the same. Yeah, but this isn't the case here with this equals, because we're getting data with this equals, and that's the main way of communication between like the runtime library, the generated code, and the runtime library in JaCoCo. To quote the documentation, they essentially tell us here quite bluntly in the design document, yeah, they wanted to support Java 1.5, and so they couldn't use any fancy methods. So they had to resort to equals. So as they tell you here, the instrumented classes communicate through the object equals method with the runtime. An instrumented class can retrieve its probe array instance with this code. Sounds kind of insane, so I dig deeper. Yay. How does this equals method look like? You might wonder. So it's essentially like, and that's the runtime data is essentially the object that is then put into the JaCoCo data field. Yeah, you have an equals method that gets the probes and then sets this array as the probes array. I think one of the entries there. Is this properly well manageable code? No. Does it work? Yes, because they've used it for like 20 years now. So please don't write such code in production in your database, in your applications. But you see, you can have fun with the equals method. And the main idea is essentially that the runtime and the generated code only communicate through standard Java types, and it makes it far easier to work, especially with old Java libraries. Then, of course, there are other code coverage tools. One of them is the code coverage tool of IntelliJ. But how does it work? It works similar, but not too similar. So the main difference is here, you might see here that instead of using Boolean arrays, we're using int arrays. The cool thing about this, every time we hit the line, we actually count that we hit the line. So an interesting fact is that it's not atomic. So what happens if we use it like in parallel? I don't know, but it's probably good enough here, they use it. And so essentially how the coverage tools then later work is that we have all these Boolean arrays, they live on the heap, and then at the end when the application is like shutting down, we just take all this information and write it out. Because we have all the Boolean arrays, we know, okay, this Boolean array value is related to this other, to this line in this file of code, so that's fine, because after all, we're instrumenting this code. So that's coverage testing. So you saw now how we could use equals in a non-standard manner and still win. Then here we have testing as a use case. And I also wondered, like, how does this work? We just write here at mock on the type, and it kind of magically does what we think. So I dig deeper, and I use my tool. For one, when we see here the code, I could see which classes were actually modified. And the classes that were modified were all the classes from the list interface up. So list implements the sequence collection interface. So this one is modified, which implements the collection interface, which implements the iterable interface. So for example, when we take this here, the for each method, in the iterable interface, we can take a look how it's modified. And so the for each, it's pretty simple what it does. It just iterates over all elements and accepts them. So this is the code that's generated for it. Yay! It's quite a lot, and I understand like most of it. But the documentation is really good in Mockito, in the internals, I can tell you. Anyway, it's a mouthful, so we'll start with the basics. We first get our mock method dispatcher. It's essentially like the Mockito way of getting like the data that we need for this specific method, like the Mockito, all the things where we store like, oh, by the way, we need to execute this action. And I assume that the hash code has something to do with the method and the class name here. Then what we do, we want to get a handle, so we want to see, should we do any action here? And for this, we check, hey, did we actually mock this? So should we actually mock the current object? And if so, do we implement this method? So I think it's overridden. I barely understand what this overridden means, but I think it's like, hey, do we actually override this method? And then what we do, if so, we get a handle from our dispatching library. And then essentially what we do, if we don't handle it, we call the method itself, because if we don't mock it, we probably want to execute it normally. And then if we mock it, we execute it here. What you might see is interesting is that if you look closely, iterable.class.get method is used twice with the same arguments. This could be field for optimization. So the tool that wrote could be used by people that are working on instrumenting agents to actually improve the thing here. But you might wonder, where is the list implementation? Because yes, list is somehow modified, but not the methods that are just abstract methods in there in the interface. They're not just interface methods. So I'll look deeper. And what did I do? I want to know which class it is. And so I used my trusty old IDE, IntelliJ, got into the debugger and checked it. And you see here that it's a weirdly named class. It's list $Mockito mock and then some long byte string. But that's essentially class implementation. And so what we can do, we can look up this class. And what we see here that it first gets a lot of methods, like a lot of method handles. And then for all methods, for example, for the add method, what it does, it just calls essentially the internal data structures and tells it, hey, please, we want to intercept this abstract method. Please do something with it, and then return some value. And that's essentially based on what you specify as a Mockito user what it should do. And another fun thing is the instrumentation class has loads of methods, and one of these is get all loaded classes. So you can tell, or you can ask your JVM, hey, please give me all loaded classes, give me all classes that you have, and we can use this to also get a bytecode of our classes. In this way, I was able to show code like this, because this class isn't transformed, it's only generated and then loaded. Now onto a live demo, I hope it works. Let's see. it's always tricky. So you see here we have a simple, oh, so you don't see it here? um, I hope it's mirroring. Let's see, cool. You see it here, it's the example from before, and I can show you when you open it. You see a whole load of methods. I essentially wrote a simple web server that allows you to interact with it, with the whole application. And of course, your test case has to run alongside, so that's why when you look closely, you saw a long threaded sleep. So we can see that we need to run it. So let's run it. So when you type this, maybe you see it here, but essentially we run it by running the tests here, and I hope it works. We just tell it, hey, please test it, and we tell it as an arc line in our tests, hey, please use this Java agent in the server mode. It's a live demo, so suspend. Okay, it worked. And so a fun thing is here, it's currently with like the later Java versions, you use the less Java likes that you attach agents dynamically. So if you use any instrumentation agents, use them from the beginning. Anyway, now this should work. So we see here the instrumenters. So we see there was one instrumenter found. It's the inline bytecode generator by bytebody. So you see Mockito uses bytebody under the hood. We can click on this and see what classes were modified, and then directly see like what I showed you before. All the methods that were modified. Essentially, we were modifying here the default implementations. And we can also go here in the Java P mode and see the same with Java P, because before you in any way report a bug report to some library and be like, oh, I found this issue, don't trust your frontline, don't trust your decompiler, but look at the bytecode itself. It takes some time to get used to, but don't waste the time of open source maintainers. So the other thing is we can look at classes, and I showed you before we can look at all classes, and that quite a lot. And we can also see here the class Mockito here with a different bind string, but it's essentially the same. So that's how the whole Mockito class look like. So for every method we get we get a method object, and then we do this for all methods. Yeah. And you can use my tool to essentially see what an agent did, and also which classes are generated, which is quite handy when you're developing agents and when you want to understand how they work. Now back to the and Michael van Keur that I told you before, who was like had the idea of this agent, he used it to find a bug in Spring, which was pretty nice. He found a bug in relates to unchecked exceptions in CGlib proxies. Not a Spring Boot developer, but it was accepted, so it was probably a meaningful bug. This was done using the plugin, and he found that the generated bytecode wasn't as nice as people were expecting. Anyway, for my last 15 minutes, I'm showing you a few more use cases. For one, I just found something that I found quite interesting with annotation classes. So consider this example. It's pretty simple. We have a simple annotation called annotation, because naming is hard, and it has a key and a value attribute. And then we have the annotation test class, and on it we have the annotation. So what we then do, we can just, in a test case, because we're still running on the test, it's easy to run here. We can just get the annotation object here. But now we're wondering, like, what is the type of this object? Because annotation is clearly an interface, so someone needs to implement it. So we can do the old trick with the IDE again and see that it's a proxies 7 class, and then we can go into my tool, because that's what my tool is for. We can check how proxy 7 looks like, and see that foreign flow really likes this method. So it's like, hey, please report this to the issue tracker. I don't have any clue what to do with this method. So no, I didn't do this because I could just see myself and see what it does. And so essentially how it works, it implements a Java proxy. Proxy is essentially a proxy for a different object. And so, for example, the hashcode method, what it does, it calls on the proxy handler, hey, this method was invoked, please. And then essentially the implementing proxy object, what it does, it's like, oh, you wanted to get a hash code, I compute the hash code in the invoke method. Or you wanted to get a field key, I get you the field key from the array. But it's not actually implemented in bytecode there, but just a method that calls all this. So the cool thing is here, the objects that you then see, they are generated by the annotation parser. Whenever the annotations are parsed from the bytecode, which is pretty neat. Then the last thing, there are of course pitfalls here. You can make errors during the developing of instrumentation agents, and one major pitfall is here class loader hierarchies. So as you might know, there's a bootstrap class loader. That's where like all the most basic classes are in. Then you have the platform class loader where like your Java runtime libraries are in. Then this class loader, then we have an app class loader where your application like lives in, loads the application, and then we have application classes, in this case X and Y. And so what's really fine is that when you have a class in the app class loader, and it uses bootstrap classes. Problem is, consider now if we have a class in the bootstrap class loader that wants access to your class X, that doesn't work because the bootstrap class loader, when we ask it, hey, give me the class X, it's like, I don't know it, but maybe one of my parent class loader knows it, but it has no parent class loader, so it doesn't have any access to X. So how we do it here is we can essentially add a runtime jar to the bootstrap class path, and that's essentially how we can implement our runtime, because in our generated, when we're doing bytecode modifications and we want, for example, use classes, we need to put them on the bootstrap class path. The important, there's a method for this, it's called append to bootstrap class paths order search, but one of the reasons why JaCoCo didn't use it was that it didn't exist back then. So if you look for Java 21, there are lots of methods. We get all the loaded classes, we can retransform, and also we can append to class loader search. So we essentially tell it, here's a jar file, please also load from these classes when the bootstrapper class when the bootloader class loader asks for something. The problem is, back in the days of Java 1, not of Java 5, some of you might remember these nice days. It was before all the stream nonsense. It was the good old times. And you're joking, but when I was at university, and I was doing things on like formal verification, they only supported Java 5 because I think it was the last Java without generics. So it was a good time. Generics made things more complicated, but of course also more readable. So you see that the list of methods is so much shorter, and one of the critical methods that's missing is like the append to class class path bootloader search. And that's a real problem, because this is the reason why you couldn't add at runtime new classes to the bootstrap class loader. And so JaCoCo didn't have a choice. They could only use basic types in there in the generated code, so that's why they misused equals. I think nowadays, if they would write it without Java 5 support, they could use this, because in modern times they could just append a nice class there. I don't know why they're still supporting Java 5, but maybe they have good reasons. Anyway, back to the presentation. So an important part here is when I worked on the meta agent and fixed it up a few days ago, I stumbled into this, that you have to load the runtime classes only after adding them to the bootstrap class path, because there are many cases where your runtime classes should also be used by your normal agent, like your agent also wants to use them because you need to communicate, so you need to make sure that before you using them anywhere, and using means like even having them like in method signatures, they are at the boot class path. Anyway, there's also, of course, a Maven plugin, because I talked with a Spring Boot person and he was like, make a Maven plugin out of it. That sounds great. And I'm like, sure. And so my tool has now a Maven plugin. The idea is pretty simple. The idea is that we might want to handle new transformers at runtime. So consider this: we have a callback that essentially prevents all the instrumentations that happening. Of course, only all the instrumentations that are happening with like the instrumentation.addTransformer method, but if some library just uses reflection to access it, I can't find it, and I find this out because IntelliJ, the coverage tool of IntelliJ, didn't work with my tool, and they use reflection to access that transformer method. So yay. And so what this does, at transformer you can return action, for example, ignore, or so the transform method is just ignored, or you can return OK, and then you can it's added. And for example, here we're like, oh yeah, we prevent you from adding this transformer, and we just ignore it. We don't fail, but we just ignore it. And this is a way where you can make sure that the user doesn't use any transformers that you don't agree with. Of course, not any malicious, because as I said, you can use reflection and everything to get rid of this, but it essentially allows you to make sure, oh, there's no Mockito, for example, snack into production. That's pretty nice. And you can easily use it with my plugin. That's like on Maven Central, where you just give it a callback class. So that's all. You'll find more about me, and I wrote a blog post on these topics at my blog at mostlynerдлess.de. You find the meta agent, which is like open source. I think it's MRT license, so you find it here in the middle on the QR code, and you find my team. And we're doing lots of awesome stuff. So if you ever wondered who implemented the new null pointer exceptions that actually tell you what happened, that was one of my colleagues. It took like 2 years, but I think it was worth it. So thanks for being here, and thank you. Maybe we have time for 5 minutes of questions. So if you have any questions, yes.
Could be slightly off topic, slightly. But we talked about agents, we talked about profiling, we love open telemetry, and then a client of mine uses Eric's Java 1.
What Java?
Eric's Java, reactive.
Oh, yes, yes.
And he is desperately trying to get a flame graph that makes sense.
Oh.
Eric's Java. Flavor reactive. Is there any tool you know of?
So the question is, so the question is about, is there any tool that can create flame graphs for Reactor? No, and run. Even for like Project Loom, where it's like it's supported now, and you've seen it at conferences for like 2 years now, and people are like, Loom is really great. don't talk to supportability people about Loom. I think profiling with Loom is still slightly worse than without Loom. For example, I think Profile doesn't have proper support for it for the individual threads, and especially I wouldn't use words on stage, but yes, you are. So if you use things like Loom or also Reactor, it's so much harder because only consider the UX that you have to develop to show like a million threads. That's impossible. You don't want to have like a billion tiny stack traces. So what do you do? So it's really hard. Reactive programming is hard. I think the people in the JavaScript web frontend world found this out like 20 years ago, and now Java has this mess, which is really nice. I'm just like, haha, I'm developing C++. Anyway, and I'm getting all these segmentation files. Yes, is there any other question here? Yes.
So we know we all love recursion. Have you ever tried instrumenting your own
Yes, the question was, have I used my instrumenter to instrument my instrumenter? Yes, the only problem is, maybe I'm fast enough to see where it, am I fast enough? There, I should have it here. Yep. Oh, yeah, you should see it here. The problem is now with the transformer is that I'm transforming the add transformer method, of course. So, but then I have a new class and that's retransformed because hey, there's an add transformer method in it. So even the bytecode instrumentation step runs into an endless loop and into infinite recursion, and it breaks the stack. And there are ways around it. So this code also checks, is this not a class in like my me.Bechberger space where all this lives? Because it causes some weird problems because you modify the classes while loading them, but you're modifying your own classes. So I tried it. It's fun, but I stopped it. I did some other really recursive stuff when I found the bug in the debugger and debugged the debugger. So there was a null pointer exception in the problem is the debugging agent on your JVM put a null in a field of some. It's a feature that nobody uses, but put a null as an exception in there when the on exception debugging, and all your debuggers crashed, and so it attached a different debugger to debug the IntelliJ debugger and see what happened. So that was really nice. Debugging the debuggers. Don't do recursive stuff. It hurts. Please don't. Any more questions? I think we have a minute left. Yes.
it came to a surprise to me that Mockito is a Java agent. I looked and it does when I run my tests, it's not registered as a Java agent.
It isn't a Java agent, but it uses the bytebody agent. And as I showed you, bytebody uses an agent and uses it. So.
But I don't have bytebody agent in the runtime of my Java.
No. So the question was, but with Mockito you don't see an agent, but you can load agents dynamically. That's why the JVM, if you look closely, it tells you like, please don't attach agents dynamically. I hate it. So it uses bytebody under the hood because it makes sense. Really, don't when you write agents, use bytebody. It's nice. Or use Java assist. Don't do bytecode modifications on your own. It's just a pain. Anyway, that's all. I'll be here till like 8, so have a nice time.